So today I want to get through this part A, and then begin part B, and we'll just see how long that takes us. I don't want to get through both parts. So how bright a star is. Now, before we get to that, what do you think? What strikes you about this? It's a photograph. What are those swirls there? They're stars. Why does it make a line? Because stars are moving. Perfect. So what would be, if this is the northern hemisphere, what would be that star right there in the bullseye? The North Star, Polaris. Perfect. So if we're about 42, 45 degrees north of the equator, this angle then, like from the horizon and up to Polaris, would be 45 degrees. Cool. What direction do they go? Counterclockwise. Very good. So these are star trails around Polaris. So this would be Polaris, capital P. And it's going counterclockwise. Counterclockwise. That'd be clockwise, so that'd be counterclockwise. Very good. Now, can you see the, like, what color and what color is that? Blue. How about this? Red. Which star has the hotter surface temperature? The blue. Very good. Yep. This is a field of stars, and the caption says they are about 25,000 light years away. Oftentimes, stars are born in like a little, what we call a star nursery or a stellar nursery. Isn't that how fun? And they form clusters. Anybody seen clusters through the telescope? Yep, clusters. There's globular clusters and open clusters. The ET that we saw, that was an open cluster. Globular clusters kind of look like a little ball. But again, we see the cool red stars, the hot white stars. Okay, so we definitely have an assortment. So not today, but we're going to talk about how that assortment comes to be in a nursery of stars. We're talking about brightness. That's one of the things we're focusing on today. So now, if this is the sun and this is the Earth, a few things about the sun. The sun is radiating energy in all directions, right? And so the amount of energy it's radiating, it's a sciencey term, it's called luminosity. So the amount of energy a star, I guess I should say the amount of power that a star is radiating is given in units of watts, which is energy per second. When you buy a light bulb, it will give you can get a luminosity value for that light bulb. You know, it's going to shoot out light in all directions. So now this little bit down here, okay, so this little ray is going to find its way. Do you remember how long it takes that, am I thinking this right? Yeah, how long does it take that light to get from the sun, once it's on the surface of the sun, to us? 8 minutes. 8 minutes, very good, yep, 8 minutes. Yep, take 8 minutes for that sun to get here, or for that energy to get here. So we're going to be talking about brightness, two different types of brightness scales. So this is important, and it is case sensitive. So a lowercase m is what these are down here. This says star magnitude. That's a lowercase m, star magnitude. How bright it is appears to us. Okay. Cool. One of the things we're talking more about it is that the farther away you are from the source of the light. So if you look over here, we have a light source in the middle of these, kind of 3 orbs, 3 spheres. Okay, we have the dark purple, I don't know what you call this, violet, kind of purple, blue. So we have 3 spheres. This sphere actually is what's his AU stand for? Remember? Astronomical unit. Yeah, that's the average distance between the Earth and the sun. So at 1 AU, this is the amount of area that sun is lighting up on the inside of the sphere, is how I think of it. At 2 AUs, notice that the same amount of energy pumped out per second is now going to illuminate the inside of a larger sphere. 3 AUs, even a larger sphere. So one of the things you know is that if you are at 1 AU, the magnitude, apparent magnitude of the sun is going to look brighter than if you're at 2 AUs or 3 AUs. It's just, that's just the way it works. It's like if you get, I have a picture coming up, like if you have a car that's shining its lights, the farther you get from that car, the dimmer those lights will appear. Now, did those car lights do anything different with how much energy is pumping out? No, it's just that you're getting farther away and the light is diluted. Yep. So, apparent brightness, apparent magnitude. Sorry, they mean the same thing. Apparent brightness is a lowercase m. The word appear is important. Appear, what it appears to you. Okay, what it appears to you. As I back up, my apparent brightness is different. Luminosity is the same. Okay, it depends upon luminosity, the energy pumping out per second, and the distance you are from the object that's shining. Apparent magnitude scale. So, don't blame me. There's a lot of things in science. Don't blame me, right? So this is the apparent magnitude scale. I can never spell apparent. So a long time ago, and I like to think of him in the middle of nowhere, you know, like the BC times, there was like no city lights to necessarily be an issue. So 120 BC, Hipparchus, okay, he came and he said that, try to make sure I get this right. This is my brightness scale. I'm going to add to it. But he's like, okay, I can see this star just barely, and I'm going to make that a plus 6.0. And this star is the brightest star I can see, and I'm going to make that a plus 1.0. So those are magnitude values. Like what? So this is the brightest. I'll just put brightest for H for Hipparchus, and this is the dimmest. Okay, but here's the deal. It's not just a 1 division. It's a factor of 10 for every time you go up. So a plus, so a plus 2, he saw those 2, and a, let's see, how do I want to do this? If we make the star of a plus 1 was this bright, the star of a plus 2 is this bright. The star of a plus 3 is this bright. Do you see where I'm going down by a factor of 10? So the star of this bright, of plus 6, is that bright, relatively speaking. The thing I passed out to you, again, like the maps that I should have given you earlier, but it works out fine. Notice that it's got the same thing going on for it. The 4, and it doesn't say plus 4, but so everybody look at your thingy. The littlest dot is 4. What's the dot next to the 4? It's 3. Is it? And it's a bigger dot. The dot next to the 3 is a 2. It's a bigger dot. It's a brighter apparent magnitude. So what is the biggest dot on here? What's its apparent magnitude? -1. I'll go ahead and erase these. So that actually sets us up for, if you go this way, it's brighter. Go this way, it's dimmer. So yep, so we definitely have things. Can you find something on that map that's a -1? Arcturus, yep, I'd say so. I think Vega's really big too. Altair, just a big dot. Capella, yep, big bright honking stars. Actually, that sort of idea, making sure you are careful to read your map, can help you when you're looking at the nighttime sky, because if you see something just really bright, look for the big dot. Okay, and kind of orient yourself that way. So yeah, that's the don't blame me sort of thing. So for stars that are dimmer than M, little m is apparent magnitude, or apparent brightness, less than 0, we have to go to negative values. And again, this kind of, it seems counterintuitive that this is a brighter object when M is minus 1.46 and this is dimmer. Okay, so this is the magnitude scale referred to on our maps. So a few more things. Let's see. Yeah, flip it over to the back, where it gives you 3 categories. Again, these come out each month because our sky will change each month. And notice there's some really good information along here. For instance, see what star did I say? We did constellations. Who was the one that saved Andromeda? Who's the character? Perseus. Very good. And what was Perseus holding in his hand? Medusa's head. Yep. And there's a star called Algol, which, if we find Algol, the star which is in Medusa's head, part of Perseus, it's under things that are seen easily with naked eye, and there it is, Algol and Perseus, a famous eclipsing binary star. Magnitude varies between 2.1 and 3.4 over a little over 3 days. So now my point here is when it says magnitude varies, it's talking about this magnitude between 3 and 4. So we say in general, I'll go ahead and I don't care about Hipparchus, but +6, the important thing there is that's naked eye. Naked eye. So the fact that we have a variable star between 0.2 or between 2 and 3, we can definitely see this in dark skies. And I'll go ahead, well, I'll erase that. All right, so here's a figure from your textbook that kind of has the magnitude scale. Again, apparent magnitude, lowercase m, apparent magnitude, what it appears. We definitely have our 0. We have Hipparchus up to 6, +6, and it's labeled here. You can see it without binoculars in dark skies. Kind of see some milestones here. Venus can be as bright as pushing -5. So the full moon, somewhere between -10 and -15, very bright. That's why it kills your eyes when you look through a telescope. Our sun is like a -27 or something like that. So the sun from our location. But now this is where I think it's interesting. So I'm 1 AU away from the sun, okay? If I am on a planet orbiting another star, it's not going to be this apparently bright, is it? No. I just think that's neat. Dim-wise, we kind of have a few things over here. What happens to your ability to gather light if you get your lens or mirror bigger? It increases. You can gather more photons. Yep. So a 1 meter telescope, which is pretty big. I think the Yerkes observatory there by Chicago, actually that big long one, that had this big one. And so it can see objects that are pushing +20 magnitude. Hubble Space Telescope, which is in orbit about the Earth, right, +30. So anyway, I think you guys got the idea. So I know some of us appreciate this constellation, Orion. Orion, remember, has kind of these 4 corner stars, and then at a slant it has the belt region, and then hanging from the belt it has the sword. And if this is the horizon, this just amazes me. If this is the horizon, the belt stars go like this, ding, ding, ding. They come up from the horizon like that. It is so bizarre. So he's kind of slanted when he comes up. I think that's neat. But superimposed on this, we see some apparent magnitudes. Does anybody remember what constellation the star Sirius is in? Or look at your map if you want to. Is it on there? Why isn't it on there? Actually, that's a question. Why do you think it's not on there? Because it doesn't rise in time for this map. I bet it's on your next month's map, so I kind of set you guys up, sorry. It actually is Canis Major, which means big dog, which he's the hunting dog of Orion. Okay. So this is the slide I was telling you about, and then we're going to talk a little bit more about this dilution of light the farther you get away. So if you were standing 10 meters from a car looking at a pair of headlights, this is what it might look like. 20 meters away, your light meter would go down. 30 meters away, your light meter would go down even further. And you can kind of think of these as basically the light from those headlights are going in all directions. And they're kind of filling the inside of a sphere, filling the inside of a larger sphere, filling the inside of even a larger sphere. That's the dilution. It's a good way to think about it, I think. So let's see. This is specifically a distance of 1 unit, twice that unit, and 3 times the original unit. If I were to kind of count squares, these are the squares that light falls on. Okay, how many squares are here? There's just 1 square. How many squares are here? There are 4 squares. How many squares are here? There are 9 squares. Yep. The way this works, it's called the inverse square law. So for instance, if I take 2 and square it, what do I get? I get 4. If I take 3 and square it, what do I get? I get 9. So each major unit you step out, it's a factor of the number of units you stepped out raised to the 2nd power. That's the dilution. The inverse, so this is called the inverse square. Now the inverse, what does inverse mean? Does anybody know? Means the opposite of, exactly. So according to the inverse square law, the light will decrease by 1 over r squared. That's the inverse part. So however much you step back, it will be less that brightness. So we put it in the denominator, raised to the 2nd power. Okay. Well, I'm not as worried about all that as probably this, the inverse square law. But so we kind of have this neat relationship between the amount of energy it's pumping out, our distance from the object, and how bright we see it. Those are what we call 3 variables, 3 different things that all kind of work together. What we like to do in science is to take related variables like those 3 things and put them together in an equation. Now, I'm not going to have you guys do any math, but I kind of want you to kind of see if this works for you. Brightness. Now remember that brightness is apparent brightness. How bright it appears is equal to how much energy it's pumping out divided by, don't worry about the 4 pi that has to do with kind of the sphere thing, divided by the distance squared. I could put it r squared, but d squared. So what happens to brightness if you increase luminosity? It goes up. You increase luminosity, okay, brightness goes up. What happens if you increase distance? If you increase distance, brightness will go down. Exactly. So that's kind of how we go. Now, one of the things we like to do with these are, I'll put them as A, B, and C. Those are 3 different variables, kind of all related like that. We like to kind of what we call rearrange the equation. And if instead, or if we want to kind of isolate luminosity, we can actually take the same relationship up here, and I kind of call it flatten it out, kind of crisscross multiply. Luminosity then would be equal to brightness times 4 pi distance squared. And we have the same sort of thing going on. If we look at this relationship, if we increase luminosity, that's going to increase brightness. If luminosity stays the same, if we increase distance, we're going to have to decrease brightness for that to stay the same. Have one more equation, it's just a rearrangement. If we're trying to isolate distance, now the fact that distance is squared, what's going to have to be is we're going to have to take what we call the square root of the whole quantity. But we can isolate distance, and this is the relationship it has with the amount of energy it's pumping out, luminosity, and the brightness as it appears. Now you might be, so like Mrs. Snipes, on our next unit exam, what am I going to have to know? And I'll try to kind of guide you through what that is. But this is you guys got the whole headlight thing stepping away, it gets dimmer, and pumping out more energy, it gets brighter. You guys got that. And that's sort of kind of what you need to take away from this. But these are the numbers to go along with that. Okay. So I said it's case sensitive. So if I was going to put an M next to these, would it be an uppercase M or a lowercase m? It would be a lowercase m. Perfect. That's apparent magnitude. Now keep pointing to my eyes. That's apparent magnitude. That's what it appears. Well, we need to be able to, and we'll be doing more of this in Wednesday's lecture, we need to be able to talk about stars and kind of remove the effect of distance. You're like, how can you do that? Well, we got to be able to do it. Sirius, the dog star in Canis Major, it's really bright. But is it really bright because it's close to us? Or is it really bright because it's pumping out that much energy? We have to kind of figure that out. We have to remove the effective distance of bright stars and remove the effective distance for dim stars that appear dim to us too. And so enters this other scale, and don't blame me. Okay, again, it's an M, but it's an uppercase M. Okay, and it's called the absolute magnitude. I always think absolute magnitude, like you're all fancy pants about it. Okay, absolute magnitude, capital M. So what, and I don't know who decided to do this. A unit I haven't talked, we talked about an AU, that's an astronomical unit. We've talked about a light year, that's the distance that light can travel in 1 year. But we haven't talked about a parsec, but has to do with an angle and everything. But a parsec related to something we already know is that 1 parsec is approximately equal to 3 1/4 light years. So is a parsec bigger or smaller than a light year? It's larger, yep, parsec's bigger. Yep. So anyway, what we do, that distance, that magical distance that we, in our own minds, remove objects to is 1 parsec, which is 3.26 light years away. Now you'd be like, I can't take Sirius and relocate it 3.26 light years away, but I can theoretically do the math and then recalculate how bright it's going to be, and that would be its absolute magnitude. Okay. So what scientists do, and they do it on pencil, paper, computers, is basically take these objects, and if this is the Earth, this is our solar system, basically we know that objects are at different distances. Basically relocate that object at 1 parsec to 3.26 light years from us and to see how bright it is. And that's absolute magnitude. And then we can kind of actually finally start to compare apples to apples, because it's what we say normalized, or it's all based on the same distance. So for example, our sun, which, what was that, like -27 apparent brightness, little m. If we were to locate it, which I don't suggest us doing, relocate it a parsec away, it would now appear as a plus 4.9. Which that means that its absolute magnitude would be plus 4.9. Okay, that's how that works. So absolute magnitudes, again, are relocating objects to 3.26 light years away from us, and then re-seeing how bright they appear to us. And then how bright they appear to us, that's their absolute magnitude. So absolute magnitudes of objects, you're looking at -10 to plus 17-ish. Okay. So absolute magnitude. It's basically, and I kind of get away from the spherical thing, put it all on the same starting line. It puts everything on the same starting line. Okay? So at that point now, if we see that something's absolute magnitude is pretty high, then its luminosity's got to be pretty high too. Okay, compared to something on the same starting line, a low absolute magnitude, that means that it must be, honestly, kind of just not putting out much energy, because we put it on the same starting line. We remove the effective distance. So that's important. Okay, so we're going to do a few slides in the next part. So this part of homework is going to be due on Wednesday when we meet. I finally figured out, so I've stopped putting my little assignment slides. Did you like the little assignment slides? Were they helpful, or was it about the same as what I have on my sheet? How many people would like to see the little assignment slides up? Okay, how many people say the sheet's about the same? I'll see what I can do. Okay, so let's take a few dip into the next part. Maybe. I just love stars. Stars are so cool. The sun is neat. Stars are awesome. It gets real sciencey though at times, it feels like. So, oh, dread. It crashed on me. Come back. That's promising. I think it just wants to be restarted. But I think we're going to be okay. Cool. Okay. You know, when we talk about classifying stars or characteristics of stars, we've already talked about stuff in here. We talked about color and temperature, and we talked about brightness just now. So we've already been kind of talking about classifying or characterizing stars. Sometimes it's hard to find women in science, but astronomy has had its moments, for sure. Wasn't there I haven't seen that movie. Yes. What did you think? Did you see Hidden Figures? Oh, man. I think it's been out. It's been a while, so I'll have to see it. Hidden Figures. And old photos I think are kind of fun. The older I get, I'm like, oh, that is so neat. So anyway, here's a group of women, and here's their fearless leader. Not, but actually I think probably the person who really led this was Annie Jump Cannon. And back in the late 1800s, they were actually getting stellar spectra. I know it seems like a long time, but spectra. On your last unit exam, you guys told me how are spectral lines formed? Which subatomic particle? It is the electrons. Remember that? And then I had the little light things up here, and you took little diffraction gratings, and you saw spectral lines. So they were getting those sort of images from stars. And these gals carefully looked through, I don't know how many, and started to group them. And we do that in science, we do that in light to kind of partition things. So that's what they did. And in grouping them, they came up with 7 types of lines that came from stars. Here's this pile, 7 piles, okay? And they ended up with 7 spectral types back in the 1800s that we still have today. And this right here, if you're kind of taking notes, however you're doing it, you're going to have to memorize each of those capital letters. Each of those capital letters is a type of a star. The O, B, A, F, G, K, M. That's a type of a star. That's your 7 if you count them. And as listed, they are listed from the hottest to the coolest. And I'll go ahead and tell you because I just think it is so. So the G, that actually, our sun is a G-type star. See what I mean? Kind of in the middle. So here we go. They looked at spectral lines. This is just a kind of reminder. Oh no, they didn't remember. I can't remember if I showed this back in an earlier when we were talking about spectral lines. So it's very small, but can you see the O, B, A, F, G, K, M right here? There's the 7 spectral types. And then do those look like stellar spectra? Hey, this is a question. So do these look like absorption or emission? How many people think they look like absorption lines? How many people think they look like emission lines? I'm not sure. Actually, they're absorption lines. They're little dark lines. Can you see little dark lines? Okay, they're absorption lines. The little electrons are absorbing energy at that particular wavelength. Yep. And if you could read this, and again, I apologize, it's pretty darn small, but these are temperatures, and this is the hottest, and this is the coolest temperature. I can't remember if I did this slide either. With the hottest environment on a star, so this is hottest, and this is coolest. Okay, with the hottest temperature, what happens is actually we get the electrons to be stripped off if it's too hot. So with those O-type stars that kind of have that classic, there aren't very many spectral lines because it's so hot that the electrons were removed from being part of an atom. Then we kind of have this assortment of things as you cool down. Again, I can't remember. I'll go ahead and say it in case it's not on one of my slides. Usually I do. I have a really, I think, easy way to remember those 7 spectral types, and it goes like this. O, B, fine, guy or girl. They both start with the letter G. Kiss me. O, be a fine guy or girl, kiss me. I don't know if it's on a slide coming up or not, but you probably get that. Probably make it to your note card too. O, be a fine guy or girl, kiss me. Or this is the hottest. Few spectral lines because it's so darn hot, and this is the coolest spectral lines. And so all this is doing is kind of showing you with those spectra, with the seven different piles that those ladies divided those things up into, this is kind of what they were seeing with those seven different groups. Now, it might be interesting. There's a good chance they didn't necessarily know why the pattern was as they were seeing, but they saw the pattern. And that happens a lot in science. You see the pattern, then you explain the pattern. So, all right. So here we go. This is hottest to coolest. Can you kind of see these dim, dark lines here? Now, one thing I didn't mention is that, maybe it says it in the caption, but you can see for the B type, I've actually, or your textbook has 2 B type spectra. So those would be fingerprints. They kind of remind me of DNA a little bit. Okay. So the B's are subcategorized, I think it's 0 to 9. So 0 being the hottest, 9 being the coolest. A couple of A's, a couple of F's, fine, a couple of girl or guy, a couple of kiss, a couple of me. So I'm impressed that those ladies could see that pattern, because to me, I'm like, I don't know. Pretty darn cool. So when we start talking later this week about stars, how they live their lives and all that stuff, how a star is born, lives its life, and how a star is going to die, we're going to see that of these 7 spectral types, that's definitely a player. Okay, so this is very important, how we classify a star. Okay, just a few more things. So do you guys remember the Doppler effect or the Doppler shift? What do we say if an object's coming towards you? Do you get a blue or red shift? If it's emitting light and it's coming towards you, you guys answered this awesome on the test. If it's emitting light and it's coming towards you, will the light be shortened wavelengths or will they be lengthened?
It's blue is shorter.
Blue is shorter, perfect, yeah, blue. And then if it's going past you,
Longer.
that'd be longer, red, exactly. Blue shift, red shift, yep. And that's all this next topic is talking about. But I think, I can't remember if this is on the test question, what about if it's moving sideways? Is there any Doppler effect? Nope. We call this, actually, is it on there? Well, we call this radial motion, radial velocity, right there. And the side to side, I actually called proper motion. And the textbook here is calling it transverse motion. So the side to side, no Doppler effect. One of the properties of stars is it moving relative to us? Okay? So we can actually understand, anticipate what the library says a stationary star of that type should look like. So those are lines. I just think this is so cool. That's information. Those are spectral lines that are created probably in the atmosphere of the star that is sending us that light. It's a fingerprint. So what if it's red shifted? Will those spectral lines go here to the left, or will those spectral lines go to the right? How many people think those spectral lines will go to the left? How many people think they'll go to the right? They go to the right. Yep, they go to the right. It's subtle, but can you see it? So is it moving away or towards us? Away. Yeah, it's moving away. Isn't that cool? It's a very subtle thing. And we can take those lines, and the faster it's moving away from us, the more the shift. Isn't that neat? Well, what about this one? What if it's blue shifted, moving towards us? Will the lines go to the left or to the left? Yep. So we have to compare it to our library sample. These lines aren't where they should be because it's moving towards us. I think that is so cool. So that was radial motion. You get a Doppler effect radial motion. Proper motion, you don't. They're called transverse motion. This actually, Bernard star is a famous star, and it has the proper motion thing going on. So I'm not sure if you can see this. This actually, I call it the flying V in Taurus, the constellation Taurus, the bull. So if we find that flying V, and these were taken, 20 years apart. This is a stationary star. Yeah. And the star that's, did I get that right? Oh man, which one? You think this is the stationary star? Is this the stationary star because it's in similar distance? No, because it looks like it. I think that's one. Yeah. I think this is the stationary star. Final answer, because it looks the similar place. And this guy is the Bernard star. It's moving. Final answer. That's the proper motion. So what's this? What asterism is it? Big Dipper. It could be the Little Dipper, but it's the Big Dipper. It kind of looks like the Pleiades through binoculars too. But it's the Big Dipper, and you can kind of see the direction that they are moving from our perspective. So this is what the Big Dipper will look like 50,000 years from now. This is what the Big Dipper looked like 50,000 years ago. So, it's kind of interesting. Well, that's as far as I wanted to get today. So good job, and we'll pick up with talking more about stars on Monday, or you know what I mean, Wednesday. But lab tomorrow.